the whole thing started by getting gamma rays from gamma ray bursts. Basically make an intermediate particle called a delta plus particle, which has mass of 1232 MeV. This is very unstable. This is an intermediate particle. It's not going to stay as a delta plus. It's not going to hang out as a delta plus for very long. It will decay to make either a neutron as in the stuff that we know and love, neutron and a pion plus, or a proton and a neutral pion. If it's a pion plus, then that pion plus will give us a muon and a muon neutrino, and the muon plus will decay further into a positron, an electron neutrino, a muon antineutrino, and a muon neutrino, all regular stuff. You can look up how a pion decays and you'll get this sort of equation. You can look up how a muon decays and you'll get this sort of equation. If muons didn't decay, we would have more muons, right? But muons decay, and that's why we have electrons. They decay into electrons or positrons, depending on which one. And then, of course, we get more electrons. And then the pion plus, because you could have also made a pion plus, remember, as an option, and then that would decay into gamma rays. So either way, in this interaction, at the end, you have neutrinos, potentially, and more gamma rays. Now, we already had gamma rays, so we're not so interested in seeing more gamma rays, but potentially, through this hadronic acceleration, you could get neutrinos. Reese! Hi, Reese. Hello, everybody. Thank you so much for joining. Welcome to the live. Thank you, Crazy Sick Wine. Thank you, Reese. Happy New Year. So basically, the leptonic theory for gamma ray bursts says that the electrons are accelerated, and those accelerated, shock accelerated, just excited to the power infinity type of electrons give us gamma rays because they do synchrotron and inverse Compton. And you can look these processes up, basically ways to lose energy and give us gamma rays. And we know we pick up on gamma rays. So of course, probably there is such things happening. But the hadronic theory of gamma ray bursts tells us that what if we allowed the protons to also be shock accelerated? So not just the electrons, but the protons, if they're also shock accelerated, then they could also become very excited and interact with photons, give us an intermediate particle of the delta plus, which then decays to give us neutrons or protons, and then pions, and then the pions will give us muons, electrons, positrons, and neutrinos. And ultimately, you would get high energy neutrinos from this process. So according to Waxman-Balcall, the authors of this type of theory, hello, approximately half the time the photomeson interaction of an accelerated proton with a gamma ray photon. So this is called a photomeson interaction, another name for such a thing. So this is the interaction between an accelerated proton and a gamma ray photon creates a neutron, and half the time a proton. So I mentioned how it can either make a neutron or a proton, right? So half the time it kind of makes a neutron and pion plus, and half the time it kind of makes a proton and a pion, neutral pion. When a neutron is created, it can escape the magnetic fields of the gamma ray burst into space, beta decay into a proton, and reach Earth as cosmic rays. So this is super important. The nice thing about creating a neutron is that it's neutral, so it can escape the magnetic fields of the gamma ray burst and go into space and beta decay into a proton, and by the time it's reaching Earth, it might be, just a proton, and basically we get it as cosmic rays. So that's super cool. We could get cosmic rays from a gamma ray burst, but of course, at that point, it might have changed. It might have bent around a little bit, and we might not know that it came from a gamma ray burst. Since gamma ray bursts are some of nature's most powerful accelerators, it is only natural to hypothesize that the highest energy cosmic rays observed with energy around 10 to the 20 eV might come from gamma ray bursts. It was theorized by Waxman